Okay, thanks everybody for tuning in to today's webinar. Before I begin, I'll just give you a little bit of background information as to what my role is at NEL. So my background is I'm a mechanical engineer, and at NEL I've got a number of different roles. So I'm quite heavily involved in the wet gas flow metering side of the business. I've also done a lot of erosion testing, and I'm also the technical lead for control valve testing, which is the subject of today's webinar. So before I begin, I'll just give you a little overview of the contents of today's webinar. So it's going to be really focused on control valve testing, but I'll give a sort of brief overview of what a control valve actually is and some of the different types and characteristics. I'll go over some concepts and definitions that are kind of key in terms of dealing with not only control valve selection but control valve testing as well. Then I'll go through some of the test procedures for actually characterising control valves, so things like flow coefficients and pressure recovery factors. And then I'll finish off with a section on control valve wear, which is basically some of the different mechanisms such as erosion, cavitation that can cause damage to control valves. And I'll have a little section on CFD modelling and how that can be used as quite a powerful tool in terms of managing and predicting performance. But the first section is going to give an overview of control valve types and characteristics. So, although isolation valves and non-return or check valves are technically control valves, these won't be the focus of today's presentation, but these can come in different types and styles. So isolation valves, they basically shut the flow off completely or allow basically 100% fully open. Non-return valves allow the flow to move in one direction only, so they basically prevent any backflow, and these can come in different types and styles. But the focus of today's presentation is pressure or flow control valves, and these basically regulate or control the rate of flow by varying the size of the flow passage. So they increase or decrease the flow area. As a result, you get a drop in static pressure, and as a result, you increase or decrease the flow capacity within your pipe. Now these can come in a variety of different styles. There's two main types. So you've got linear motion, so things like plug valves, and then you've got rotary motion, so things like ball valves and butterfly valves. So some of the pictures here, the one on the left is a ball valve, and that's basically a circular or spherical ball. It's got a cutout through the middle, and as you basically rotate the angle of the ball, it increases or decreases the flow area. The butterfly valve is basically a disc mounted on the central stem, and as you adjust the angle of the disc, it exposes the flow to basically more area. One of the quite common types of control valves in the oil and gas industry is the choke valve. So this basically controls, or is commonly used to control the flow rate from an oil and gas well. And these can come in different types and styles, but one quite common one is a cage choke valve. So you've got a cage on the inside of the valve that's basically got holes bored through it, and you've got a central plug, and that moves up and down the cage, and as a result it exposes more of the flow to a larger area. So loads of different types and styles, and it really depends on the specific process application, what design you go for. Now, depending on what type of valve you choose, they can have very different opening characteristics. So this is quite an interesting diagram. On the bottom x-axis, you've got valve travel as a percentage, and on the y-axis, you've got flow capacity as a percentage. Now, if you've got a valve with a linear characteristic, that basically means for a certain amount of valve travel, you get an equal increase in flow capacity. So 50% of the travel gives you 50% increase in capacity. But you might have a requirement for a very fast opening valve. So you would choose, for example, a fast opening globe. So that means for very small increases in valve travel, you get large increases in flow capacity. On the opposite side, you might want much finer control down at the very low opening positions of the valve. So you probably use something like an equal percentage valve, which gives you much finer control at the lower portion of the valve travel, and then it's an exponential increase as you open it further up to to 100% of travel. If you've got a control valve, you need some way of actuating it, and an actuator is basically what moves or operates the valve by receiving a control signal. So these can come in all different shapes and sizes. You can have basically pneumatic actuators that are powered by air or some kind of gas. You can have hydraulic actuators, and you can have electrically powered actuators as well. They're often combined with a manual sort of hand wheel or lever that allows you to manually open and close the valve. And some of the things you need to consider with an actuator are the opening torque. So what's the torque required to actually basically move the valve from a fully open to a fully closed position? One thing that's quite critical for actuators is the failure mode. So for example, if you've got an electric actuator and you have a sudden loss of power, what does the actuator do when it basically loses power? Does it fail with the valve in the same position it was last in, or does it fail with the valve fully open or fully closed? To give you an example, some of NEL's test rigs are very high pressure, so our actuators fail open, because if they didn't, it could lead to basically a dangerous build-up of pressure. But on the other hand, you might have some process requirements where you want to basically contain your process fluids, so in those instances you might have the actuator fail in the closed position. So when it comes to actually selecting a control valve for a specific duty, there are numerous different things you need to consider. This is just a snapshot of some of the sort of key ones. So things like the flow range. Is the valve suitable to cover the flow range that you require? Temperature and pressure. Is it going to be high pressure application? Is it going to be cryogenic service for the valve? You need to make sure the materials in the body can withstand that. Fluid properties are important. So if you've got liquids or gases, some types of valve seal are not compatible with certain oils, so you need to kind of bear that in mind. Things like allowable leakage. This is more for if you're using the valve as an isolation valve. There are different classes of leakage, so class 1 to class 6. Again, it depends on the process requirements. If you're using the valve with gas, you'll probably want a higher leakage class versus if it was just to be used with water. Things like noise limitations. So what are the environmental noise limits? Control valves can be fairly noisy because you're obviously using them to induce quite large pressure drops, and you need to make sure that the noise that's produced from the valve is not breaking any sort of regulations. There's obviously safety implications as well. And things like the piping system that you're actually going to install the valve in. So what's the size of the piping? What's it rated to? What are the flange types, the process connections? All of these things you basically need to take into account when selecting a control valve. Now, it might seem overwhelming that there's a lot of different things you need to think about, but valve manufacturers and suppliers are actually quite good at recommending specific valves for your chosen duty. So what they'll do is they'll give you a process sheet. You'll fill in all your process requirements, send it into them, and they'll be able to recommend a suitable valve. But it's always good as an end user to just have a basic understanding of some of the things that go into control valve selection. It just gives you confidence going forward that the valve you select is going to perform the duty. So that was just a brief overview of control valves and different types. If you want any more detail on any of the things there, you can obviously send in some questions. But now I'm going to go over some concepts and definitions that are important not only for control valve operation and selection, but if it actually comes to doing a flow test of a control valve, they're fairly important concepts. So the first one that is really important to have an awareness of is flow coefficient. So if you've ever seen a valve brochure or a valve data sheet, you've most likely seen CV values. The CV basically expresses the performance capability of a control valve. It's calculated based on the formula here. So Q is your flow rate, SG is your specific gravity of your fluid. You can simplify that to 1 if you're using water. And delta P is the differential pressure across the valve. Now, although CV normally appears in literature and brochures without units, it's not actually a dimensionless coefficient. So the definition of CV is the volume of water in US gallons per minute that will result in a 1 psi pressure drop across the valve at 60 degrees Fahrenheit. Now, it's independent of valve size or type, so that basically means for any given flow rate, if you have the CV value, you can calculate the expected pressure drop across the valve. So basically, CV is the main sort of term that's used when you want to size a control valve for a specific pressure drop or flow rate. Choke flow is another term that's quite important. The choke flow is where you get vapor formation within the valve that is so large and so excessive that you don't get any further increases in flow rate by increasing the differential pressure across the valve. So the little graph here is a good illustration of this. So it's got flow rate on the y-axis, you've got the square root of the differential pressure on the x-axis. Under normal, non-choked conditions, this relationship is a linear straight line. As you start to get vapor formation within the valve, this line starts to taper off, and eventually you'll reach what's known as the choked flow rate. So you get no further increase in flow rate with increasing differential pressure. So choke flow kind of leads us on to cavitation and flashing. These are some terms you might be familiar with. So what is cavitation and flashing? Well, to illustrate this, we've got a typical pressure drop graph. So you've got fluid pressure on the y-axis, you've got the distance along the flow stream on the x-axis. So obviously, at the inlet of the valve, you've got a static pressure. As the flow moves through the valve, the area reduces and the pressure drops. You reach a point which is known as the vena contracta, which is the lowest possible pressure within the valve, so the point of the narrowest flow restriction. And then you get pressure recovery after the vena contracta. Now, for cavitation, what happens is you've got an inlet pressure, and the pressure drop's great enough that it actually drops you below the vapor pressure of your fluid. So the vapor pressure is the pressure at which vapor bubbles start to form within the flow stream. Now, as the pressure recovers, if the recovery is great enough to take it above the outlet pressure, these vapor bubbles that are formed actually collapse and implode. And this action of implosion can actually be quite damaging to the valve. It can remove material and it can lead to significant noise levels. Flashing is slightly different in its formation of vapor, but the pressure recovery is not great enough to take it back above the vapor pressure line. So you get a mixture of vapor and liquid that continues downstream of the valve. Now, these two phenomena are generally undesirable. They both lead to significant noise emission. For cavitation, you can get significant vibration of the valve. For flashing, because you've got this imbalance between the liquid and vapor phases, it can vibrate the entire pipeline. And both of them result in material loss in the valve. So cavitation is erosion due to the collapsing vapor bubbles, which cause shock waves and as a result remove material. And in flashing, it's liquid droplet impact on surfaces, which again results in material loss. So this leads us on to liquid pressure recovery factor. Now this number, again, you'll probably see in valve brochures and literature, and it basically describes how well the valve recovers pressure. You know, once the pressure drops to its lowest point, how well does the valve actually basically recover the pressure that was lost? It's calculated using this formula. So some of the terms here, Qmax is basically your choked flow rate. C is your flow coefficient. N1 is just a unit conversion. This formula is actually taken from the valve test standard. So that's why there's a unit conversion term in here. P1 is your inlet pressure, PV is your vapor pressure. The density ratio is just your specific gravity, and FF is a correction factor. So the key thing to understand about the pressure recovery factor is the higher the FL number, the worse that the valve is at recovering pressure. So ball valves have very good pressure recovery, so they've got lower FL numbers. Globe valves tend to have weaker pressure recovery, so they have higher FL numbers. But the important thing to note here is the lower the FL number for the valve, the more likely it is that you will see cavitation within the valve. So ball valves and butterfly valves tend to be more susceptible to cavitation, whereas globe valves are much better at dealing with basically the presence of cavitation. Another term that's also used to describe cavitation is the Cavitation Index. This is the ratio of the inlet pressure minus the vapor pressure divided by the overall pressure drop across the valve. Now, it's a little bit back to front with the Cavitation Index. The higher the number, basically the less likely or the less intense the cavitation. So to illustrate this Cavitation Index, or sigma, we've got a graph here. So on the y-axis, we've got acceleration on the valve body. This is basically the noise level, but you can think of this as the intensity of the cavitation. And you've got sigma on the bottom. So if you read the x-axis from the right to the left-hand side, so the higher the sigma number, the less intense the cavitation. And it's generally accepted that the sigma value can be split up into different regions of cavitation or regimes. So if you've got a very high sigma number, you've got no cavitation. You then start to have small bubbles forming within the flow stream. This is what's known as incipient cavitation. And then you move into constant cavitation, where you have mild, steady popping or cracking of the vapor bubbles, so it becomes more audible. Incipient damage, sigma, is where you get minor observable damage on the valve surface, and you get increased vibration and noise. The vibration levels will reach a maximum, and you'll have significant damage at this point as well. And then you get what's known as choking cavitation damage. So this is basically cavitation's fully developed. You might get a slight drop in noise levels because the vapor formation is so large that some of these vapor bubbles actually absorb the noise levels. But at this stage, you get no further increase in flow rate. So your flow is fully choked, and you've got significant cavitation damage. So this is a typical globe valve example that you might see in a valve brochure, and it basically gives you sigma values, and so you as the end user can take your process inputs and you can calculate a sigma value, and if it lies within a certain range, the manufacturer basically suggests that you're likely to get cavitation within this valve, so you might want to invest in some cavitation control, right down to basically flashing. And obviously, most of the time you want to avoid cavitation. There are special valve designs that are basically built to withstand basically to limit the damage caused by cavitation. So before I move on to actually talking about valve flow testing, I thought I'd do a quick sizing example, just basically to show you how to use flow coefficient values in practice. So you might have seen flow coefficients in valve brochures and data sheets. How do you actually use these to basically select an appropriate valve? So the example we've got here is a water storage tank. So it's got a control valve on the bottom of the tank, which is open to atmosphere. And you've got a variable water level from 5 to 40 metres, and you want a constant water flow rate of 100 litres a second. So you need to determine a CV range for this valve that will allow you to achieve 100 litres a second at any water height between these two values. So if you remember the flow coefficient equation, you can simplify the specific gravity to 1 in this case because it's water. The maximum CV will occur at the lowest possible basically pressure differential, so that's when you've got 5 metres of water head against the atmosphere. So you plug in the numbers, so 100 litres a second is 1585 US gallons per minute. The 10.3 and the 14.5, they're basically to convert 5 metres of water head to bar and then to PSI, so it's just unit conversion. And you get a CV of 597. On the other hand, the minimum CV occurs at the largest pressure drop, which is 40 metres head. And when you plug that in, you get a CV minimum of 211. So you need a valve with a CV range of 211 to 597 in order to basically achieve 100 litres per second flow at any height between these two values. So that's great, you've got a CV range. What would you do next? Well, you might go to a valve brochure and be presented with a table that looks like this. So this is a table of CV values. So on the left, you've got the valve size, and at each column, you've got different opening positions of the valve. So this is a butterfly valve example, so it's from 10% open to 100% open. And you can see that the 6-inch valve here would be quite a good choice. The CV range that you're looking to cover falls within the middle third of the valve travel. It's generally a good idea to avoid using valves in the lower 10% and upper 20% of their travel, just because they're much harder to control at these extremes. And you want to avoid using a valve that's not less than half of the size of your pipeline, because that can obviously cause issues with excessive pressure drop, and obviously you need to basically reduce the size of your pipeline down to accommodate the smaller valve. You'll also notice that I've highlighted in red here that this table actually provides FL numbers, so the pressure recovery factor, and a little bit later on in the webinar I'll have a worked example to show you how you actually use FL numbers in practice and basically what they're used for. So now I'm going to move on to control valve flow testing. So this is work that NEL is quite heavily involved in, and I'll just go through basically the test procedure and why you actually test valves in the first place. So some of you might be thinking, why bother testing valves? You know, if a manufacturer's giving me CV data, is there any point in actually doing it? Well, flow testing actually provides the end user, confidence that the valve that they've selected is going to meet its intended duty. So a lot of the time we'll test a flow valve, and yeah, it will tie up quite well with the manufacturer's performance data, but other times we've tested valves and there's been quite a significant difference between what the manufacturer's claiming and what we actually see during a test. So it's really beneficial, especially if it's for subsea service. You don't want to come across problems after the valve's been installed subsea, because the expense of basically removing a valve and rectifying a problem can be significant. Valve flow testing can also highlight any issues with the design of the valve. So a lot of the time we'll have valve designers or manufacturers, they'll actually come to us at the design stage to do some flow testing, basically to try and characterize the performance of their design. If they come across any issues in the design stage, they can obviously rectify it at that point before the valve's been deployed or sold, and it's obviously much cheaper in the long run to rectify problems early on. And valve testing can also be useful for predicting safe operating limits. So that's more related to the pressure recovery factor number, which is related to choked and cavitating flow. So when it comes to testing or flow testing valves, so basically how do you determine flow coefficients and pressure recovery numbers, so FL numbers, there are two main test standards. So the top one's the American standard, the bottom one's the European standard, but they're essentially the same thing. So the test procedure that's contained in both is almost identical. So once you've decided to test your valve, you obviously need a flow facility. So NEL's water facility would be a good choice. This is an example of a globe valve being CV tested in the facility. So you can see the upstream and downstream pipework. As NEL, we're the holders of the flow measurement standard for the United Kingdom, so that means all our test rigs are fully traceable. We're actually the primary standard, so everything has got low uncertainty, which makes it obviously perfectly placed to perform CV testing. So what are some of the test considerations you need to look at? So in order to flow test a valve, you need to obviously install it within the line, and the upstream and downstream pipework are quite important. You want to basically have pipework that matches the internal bore of the valve. You don't want any large changes in bore or steps in bore, because that can affect the pressure drop measurement. If you're establishing the flow coefficient, you need to obviously determine flow rate and pressure drop. So in order to basically measure pressure drop, you need pressure tappings within your pipework. Now, the standard dictates that the pressure tappings should be 2 diameters upstream and 6 diameters downstream of the valve body. The reason for this is, if you took the pressure drop directly across the body, you might actually still be in a stage of pressure recovery. So as a result, you might measure a larger than expected pressure drop across the valve. Basically, what you want to determine is the overall pressure drop across the valve. So that's why the 6 diameters downstream basically gives the pressure time to recover. Another thing that's quite important with pressure tappings is the dimensions. So there's a phenomenon that's known as static hole error, and this is basically the error in the pressure measurement because you basically bored a hole through the pipe to take the measurement itself. So the way you minimise that is obviously having as small a through hole into the pipe as possible, and the standard actually has guidance on what size of hole you should actually use depending on the size of your pipework. And you also need to have instrumentation to measure the differential pressure and the reference flow rate. So for any else water facility, we've got reference weigh bridges that we can use, or we've got reference turbine meters that have a fairly low uncertainty. So these are some of the things you basically need if you're going to set up a valve flow test. So once you've set up the valve, it's installed in a test line. How do you actually determine the flow coefficient? So for every opening position of the valve, you set up test conditions that result in 3 different differential pressures across the valve. For NEL valve testing, we tend to do 1, 1.5 and 2 bar across the valve. And then at each of these differential pressures, you obviously record the flow rate, and using the CV formula, you can obviously calculate a CV for each differential pressure. The reason we do 3 different differential pressures is, even though they're different, obviously, flow conditions, as long as the flow area remains fixed within the valve, you should roughly get the same CV value for each point. So we take 3 and then we average the 3. If any one of these points deviates from the average, that can indicate the presence of cavitation or flashing. So during a CV test, you don't want basically little to no cavitation present. The way we do that in the NEL facility is we make sure the inlet pressure to the valve is high enough that even though we've got, say, 2 bar across the valve, we're not dropping below the vapour pressure of the fluid, so we're not forming vapour, and as a result, we're not inducing any cavitation. So once you've done that for every opening position of your valve, you might end up with a graph that looks like this. So in this case, on the y-axis, we've got stem positions, but just think of this as basically valve travel from 0 to 100%. On the y-axis, we've got the valve flow coefficient, and you can see in this instance that the test data and the predicted performance data tie up quite well. So the dark blue data was basically the manufacturer's predicted data. The light blue is the NEL test data, and you can see, there's some differences, but they match up fairly well. So this gave the end user confidence that, yep, this valve is going to meet its intended duty. On the other hand, this is another example of a valve that we've tested. So this was a choke valve, and you can see at 100% opening capacity, there's actually a 20% deviation between the predicted data and the NEL test data. Now, 20% is not insignificant. A valve will be sized for a specific process requirement. Things like pumping capacity and all that sort of thing would be dependent on components within a process system. So if a valve is actually going to result in a larger pressure drop than you originally intended, that can have significant consequences. So this is just an example of the benefits of valve testing. It shows you that predicted data is not always 100% accurate. So once you've established the flow coefficient of your valve, a lot of the time manufacturers also want to look at FL testing, so pressure recovery factor testing. And the way you determine the FL number is you first take a data point with a high inlet pressure to the valve and a low differential pressure. So basically this is a flow point under normal conditions. You're not trying to choke the flow, you're trying to avoid cavitation as much as possible. You then take another data point at the complete opposite extreme. So you're trying to basically choke the flow, induce as much cavitation as you can physically do within the test facility. The way that's done is in the NEL facility, our facility control valves downstream are fully open. We increase the pump speed to a maximum. So basically, we're trying to induce a very large pressure drop across the valve with little back pressure. So we want to try and generate as much cavitation as possible. Once you've got these two extremes, you can then plot data points in between both conditions. And you'll end up with a graph that looks something like this. So the blue data points are your flow rate data. So this is flow rate squared on one of the y-axis, so the left-hand y-axis. And you've got differential pressure on the x-axis. So if you remember back to the choked flow diagram, under normal non-choked conditions, the relationship here should be a straight line. And you can see from the first 5 data points that's the case, but the 6th data point starts to deviate from the straight line. This is because you're starting to develop cavitation within the flow stream. So for FL testing, you basically want to determine when the data starts to deviate from that line. So on this graph, you can see roughly where that occurs. For each of the data points, you can also calculate an FL number, and you can fit a curve through that, and then you can draw a line up and then across, and that gives you basically an FL number. So this is the FL number here is what's known as the FLA limit. Now this is something you might not have seen before, the FLA number. This is the point at which cavitation is just starting to make itself known hydrodynamically. So that basically means when the points start to deviate from this straight line. It's not the maximum FL value, so a lot of the time you'll see FL values published. These are actually the maximum FL value. The reason we don't quote this number is if you operate a valve at this point, you can get significant noise levels and you can get significant cavitation erosion, so it's not a safe operating point for the valve. So the FLA number, if you remember back to the sigma graph for the cavitation index, it lies somewhere between the constant cavitation level and the choking cavitation condition, so it's somewhere within this region here. So once you've actually determined an FL number, how do you actually use it for predicting safe operating limits for your valve? Well, it's quite a simple formula actually. So the formula is presented here. So the delta P we've got here is the choked or the cavitating pressure drop. So this is the pressure drop for a given set of input conditions that will lead to cavitation and choked flow. FL is the liquid pressure recovery factor. P1 is the valve inlet pressure. FF is basically just a correction factor, and that's based on the vapor pressure of the fluid and the critical pressure of the fluid. So these are basically numbers that you can go and look up or calculate. So there's just a quick worked example here to show you how to actually use FL numbers. So you've got a valve within your process, and you've got an inlet pressure to the valve of 140 bar. Your fluid is water at a temperature of 20 degrees, and the FL number for your valve is 0.9, so you've either determined that from literature or through experimental testing, and you require for your process a differential pressure or a pressure drop of 120 bar. So what you need to know is, if you operate the valve at this condition, is there going to be choked flow, is there going to be cavitating flow? So you plug these numbers into the equation and you get a pressure drop of 113.4 bar. So that basically means for your input conditions, if you have a pressure drop of 113.4 bar, you're going to see cavitation, you're going to see choked flow, but you require a DP of 120, which is obviously greater than this number. So cavitation or choked flow will occur at this pressure drop, so it's not recommended that you operate the valve at this condition. So you then might have to go back and say, well, what can I do? Can I increase the inlet pressure, or can I choose a different valve design that's more resilient to cavitation? But it just shows you the usefulness of the pressure recovery factor in determining safe operating limits. So that covers control valve flow testing. I'm now going to have a section on control valve wear. So what do I mean by control valve wear? Well, this is just basically anything that can result in a loss of material on the control valve. So basically things that damage the control valve. These are some of the main wear mechanisms. I won't go through every one of these in detail, but I'll talk about some of the main ones. So corrosion is by and large the most common cause of wear in valves. So this is where the materials of the valve react with their environment, and which leads to material loss. So this can have significant impact on valve operations. So things like hand wheels can seize due to excessive corrosion, which means you can no longer operate them. It can increase the surface roughness of basically the internals, so it can reduce the valve CV. What that means is you might get a larger than expected pressure drop through the valve if you've got significant corrosion. And in serious cases, obviously the material loss can be so great that it leads to loss of containment of your process fluids or your gases. Abrasive wear is another quite common wear mechanism, and this is where sand or other particles get stuck in between sliding or rotating surfaces. So the example here is a ball valve. Sand has got trapped between the ball and the body of the valve, and as the valve is operated, the sand basically rubs against the ball and it removes material. And this, again, can be quite serious. So here's a couple of examples of abrasive wear, and in this case, it's led to loss of containment. So there's obviously leaks coming off this valve, and this is due to sand erosion. Particulate wear is wear due to solid particles impinging on valve surfaces at high velocity, and it's this action of impingement that removes material. It can be dependent on the type of particles, so the shape, the hardness, but by and large the most important factor is the particle velocity. So the wear or the damage is a function of velocity to approximately 2.6, so it's an exponential relationship. But to give you a rough idea, if you double the velocity of the particles, you get roughly 6 to 8 times more erosion. So if you can reduce velocity, it can massively help with particulate wear. Here are some kind of extreme examples of particulate erosion. So this is an internal from a choke valve. So this is the cage from a choke valve, and you can see that particulate wear has led to significant material loss. So this valve would no longer operate as it was originally intended, and you're not going to get the same level of control as you would have when the valve was brand new. So it just shows you, people don't often think that sand can actually cause that much damage, but over time it can lead to quite significant material loss. This is another example of wear on a choke valve. So this time it's the choke valve plug. So this is a plug that's moving up and down in a central cage. And you can see from the image on the right that sand has actually cut grooves within the plug. Again, this material loss is going to affect things like the valve CV, and it's also going to affect its operation as well. Now, cavitation that we've talked about at length is obviously another wear mechanism, and this is where, to reiterate, it's where vapour formation is in the valve and the vapour actually collapses. The shock waves impact on surfaces and remove material. The example on the right isn't actually a valve, it's a multi-orifice plate, but you can see around each of the orifices you've got material loss. The bottom half of the picture is actually a CFD model, which is trying to basically replicate the test conditions. So, how do you actually reduce the effects of valve wear? Well, if you've got particulate erosion, if that's going to be an issue, by and large the best thing you can do is reduce the velocity, because obviously the exponential relationship means velocity reductions give you massive reductions in material loss. You can choose materials that are wear resistant, so things like corrosion resistant steels like stellite. You can, for erosion resistant materials, there's things like tungsten carbide. These materials can have their downsides though, so tungsten carbide is very erosion resistant, but it's also brittle, so you've got to manage basically the positives and negatives of using specific materials. If cavitation is going to be an issue, then you can choose valves that are cavitation resistant, and you get valves today that have multi-stage valve trims, so the internals of the valve, rather than one large pressure drop, it breaks the pressure drop up into smaller chunks. As a result, you don't drop below the vapor pressure of the fluid, so you avoid cavitation. But more often than not, wear is just something you've got to live with a valve. You know, they've obviously got a limited lifespan, especially if the valve is going to be used in sandy service. And one thing you can use is CFD and physical testing to try and predict and manage the erosion. So that brings me on to the final section of the webinar, which is talking a little bit about CFD testing. So what is CFD testing? So it's computational fluid dynamics. So the way you actually perform a CFD simulation is you take your geometry, so in this case it's a check valve, you define it, you then define the fluid zone, so the area that the fluid occupies, you break this up and discretize it into smaller chunks, which is known as the mesh, and then the CFD code iteratively solves the Navier-Stokes flow equations, and then you can present a solution. This could be, you know, pressure drop through the valve, or it could be things like you want to determine contours of erosion or material loss. So this is an example of the check valve. It's actually a section's been cut through it, and these are actually contours of erosion. So areas in red are areas of high material loss, areas in blue are areas of low material loss. So this was basically a research project that wanted to know, you know, for a given input conditions, for a given sand concentration, what's the effect on the valve. This was another example of a gate valve, and the manufacturer wanted to know if flashing was going to occur under certain test conditions. Now the reason they used CFD rather than, you know, a physical test was the valve was particularly large and it was already installed and it was actually being used in service, so it was cost prohibitive to actually remove it and do a physical test. So that's where CFD is kind of advantageous. So this image here is basically a plot of the flow path through the valve, and it's been basically shaded in terms of velocity of the flow lines. So areas in red are high velocity, areas in blue are lower velocity. Now CFD is obviously a very powerful tool, but it's not infallible, especially when it comes to erosion testing. So it's very good at determining areas of erosion and hotspots of erosion, but sometimes when dealing with the exact magnitude of the erosion, it can be slightly off, especially if it's an exotic or a new type of material. But one way you can actually improve the performance of CFD models is to combine it with a physical test. So the picture here is a 3D model of NEL's erosive flow loop. So it's a sandy water flow loop, and we use this to test valves and other components under basically sandy conditions. We use it to do things like simulate field life of components. So we do accelerated testing, and we can use tools such as dimensional measurement and weight loss measurements to basically characterize material loss for given field conditions. So you can actually use the data from a physical test to update and tweak your CFD model. This example here is, again, an internal for a choke valve. So on the left, you've got the CFD model, and on the right, you've got the actual physical object that was erosion tested. So you can see that there's significant material loss, and the data from the physical test was used to update and tweak the CFD model. One of the advantages of this is you can flow test a smaller prototype. So you might have a large valve that you want to determine its basically a lifespan within the field, but it's just not feasible to test physically. But if you test a smaller version of that, use the data to basically tweak and update your CFD model, so basically develop material models for that specific valve. You can then apply the CFD model to much larger geometry with greater confidence in the data that it's going to produce. So that's the end of today's webinar. I'll just quickly go over what we've covered. So we had a section at the start, which was basically an overview of control valves, some of the different types, the opening characteristics and different styles. We covered some key concepts and definitions, so things like flow coefficient, choke flow, cavitation, flashing, that sort of thing. We then talked about flow testing, so how you actually set up a valve for a flow test, how you determine CV and FL numbers. And then we talked about some of the different wear mechanisms that can actually cause damage in control valves, and we finished on CFD modelling and how that can be used as a predictive tool for things like valve life in the field. So that's the end of today's webinar. I'm going to pass you back to Marietta, but if you've got any questions on anything that I've talked about, please send them in and I'll endeavour to answer them.
Okay, thanks for that, Tariq. If you'd like to ask any questions, if you could just submit them through the chat or the Q&A function. If you just give us a couple of minutes while we pull some of these off. I think we've maybe got time for a couple of questions anyway, Tariq. In the meantime, we've put a list up of some forthcoming events where any of you are going to be at. You'll also see our next webinar is the 21st of August on the topic of density. So is there anything there, Tariq, that you want to answer? As I said at the start, if we can't answer your questions today, well, Tariq will be able to take some time out afterwards and get back to you with the answers.
Yeah, we've got a couple of questions here. So someone has asked, can you explain the differences in choke flow in a gas versus a liquid? So choke flow, when you're dealing with gas, is actually slightly different. This is where the velocity of your gas is approaching sonic conditions, so it's approaching the speed of sound, and this basically means you can get no further increases in flow rate by decreasing the downstream pressure for a fixed upstream pressure and temperature. So it's a bit confusing because choke flow in liquid and choke flow in gas actually mean different things. A better term for liquid choke flow is probably limiting flow, but that's what it means when you're dealing with a gas system. We've got another question here, which is, how do you simulate field life in erosive conditions for a valve? So the way we do that at NEL in our test rig is, well, the main way we do it is increase the sand concentration. So in the field you might have a valve and the sand concentration is, a fraction of a percent. It's obviously not practical to test that in the lab because you're probably going to get little to no erosion over many hours of actually test work. So the way we accelerate basically the damage in the valve is to increase the sand concentration. So it might be 0.1% in the field. We'll test at 3 to 5%, and up to about sort of 10-15%, you can effectively accelerate the erosion and then scale it back to determine the lifetime of an asset in the field. Once you get above sort of 10-15% sand concentration, you start to get particle-to-particle interactions, and you can actually get less erosion than you might expect. But as long as you don't go above sort of 10-15%, then you can effectively, basically accelerate the wear and predict field life.
Okay, I think maybe time for one more.
Yeah, there's another question here, which is, can you explain what the XFZ number is in relation to valves? So the XFZ number is actually related to cavitation, so it's the coefficient of incipient cavitation. So if you remember the sigma plot, which was basically the different regimes of cavitation, the XFZ number is basically when cavitation is just starting. Now, the XFZ number cannot be determined through flow rate and pressure drop measurement. You have to use acoustic measuring equipment or accelerometers. Sorry, that's a bit of a tongue twister. Because the cavitation is so small that it can only be detected audibly. So the XFZ number is basically the differential pressure when cavitation is just starting over the inlet pressure minus the vapour pressure.
Okay, right, thank you for that, Tariq. I think we've just run out of time there, and I see there's a couple of other questions that have just come in, but as I said, Tariq will get back to you separately offline. So, ladies and gentlemen, that concludes our event for today. As I mentioned at the start, we will be sending you out a copy of the presentation and recording, and we'll get that to you either the end of the week or next week, early next week. If you would like further information, in the meantime, you've got Tariq's email address up there. You can also visit our website. So, on behalf of your presenter, Tariq, I would like to thank you for your time and for joining in today's event. You may now disconnect, and once again, thank you and enjoy the rest of your day. Thank you.